And it's our great pleasure to have Brenhin Keller speaking at our seminar. And Brenhin started his academic career back then as undergraduate student at Cornell University. And then he moved to Princeton for his master's and PhD work with the thesis topic of geochemical evolution of Earth's continental crust, which in this talk he will talk a lot about. And after that, he moved to Berkeley Geochronology Center and at UC Berkeley, and did a postdoc there for 3 years before he became assistant professor at the Dartmouth College since 2019. And with that, I will give the rest of the time to Brenhin Keller to talk about his work, and then we will leave more time for interaction with the audience. And this is not a formal seminar. It's like semi-formal. That's why you are not wearing anything formal, and neither do we. And so feel relaxed, and it's more like a chatting, talking time, so that the people could have more interactions. And I think we are moving from the formal Go Schmidt style talk to the golden conference style conversation. So with that, I will leave the rest time for you.
Thank you. Thank you for having me. Thank you for the very nice introduction. And I guess, could you remind me real quickly just what time I should aim to wrap up and take questions, or will we just have questions throughout? What makes sense?
Yeah, there's no specific time set. Normally, a speaker talk about 30 to 40 minutes, but you are free to end any time that you would like.
I'll try not to go too long. Well, thank you very much. So what I'm talking about here today, hopefully this is all working here. Let me minimize my zoom. Well, that's okay. So what I'd like to talk about today is sort of a really high-level overview of some of the results I found over my my time working in essentially the data science side of geochemistry, which for me was I somewhat got into by accident, basically. When I was starting my my grad school, my PhD with Blair Shaney, he had just been hired. So his wet lab, his uranium-led TIM zircon geochronology lab, had not yet been built. So I was trying to look for other things to do in my first year of grad school, and sort of stumbled on a project that ended up taking over my whole PhD and basically my whole career since then. It's been a lot of fun. I think we've learned some things. A lot of the techniques I've used mathematically and in terms of computer science have been really very simple, but there is a lot of low-hanging fruit in this field. So a few of the potential take-home points that I hope to get across today. One of them is about understanding the formation and evolution of Earth's continental crust, which we all live on. The continental crust is important for a lot of reasons, but one of them is that it's the boundary between the surface Earth system, which includes, you know, the biosphere, the atmosphere, the hydrosphere, everything like that we all depend on for life. It's the boundary between that and the deep solid Earth, which is where really most of Earth's mass is, and that really consequently provides a really major long time scale constraint on the composition and the evolution of the surface Earth system. Second point is just as a case study of what can be done with existing freely available geochemical data sets. And one take-home point here that I think is still true today, even though some time has passed, so there's plenty of fundamental exploratory science to be done with freely available public data sets. Okay, so let's get into it. I think you folks all know about what this cartoon is trying to show. Just a cross-section of some segment of the Earth where you can see a lot of the sites of magmatism on Earth today here highlighted in the modern plate tectonic system. There's a few different types of melt generation. You know, it's not usually that you're increasing the temperature of solid rock, despite what people who aren't geologists might often think. Instead, usually we're decreasing the pressure of the mantle or adding water to the mantle, and that decreases the solidity so you can melt. In all of these cases, we're taking material from the mantle and putting it into the crust. But there's a rather large difference between the crust that's made under the ocean, this or thin oceanic crust, and this thicker, more felsic continent, higher elevation, subaerially exposed continental crust. And in particular, this difference in composition and difference in density is supported by a difference in mineralogy. So in the oceanic crust, you have more of these things at the bottom of the screen, your mafic, olivine, pyroxene, some plagioclase. In the continental crust, you have some of those as well, but you also have more of your higher silica minerals, your quartz, your orthoclase, and your plagioclase, which helps maintain the buoyancy of Earth's continental crust relative to the oceanic crust. So really this continental crust in part is high and exposed to weathering and all that because it's less dense. In part it's because it's thicker. These things work together, but really this is somewhat unusual in other solar system bodies. So here we just have a look at the hypsometry of several different solar system bodies. So it's, if you're looking at the elevation relative to some gravitational equipotential surface, a surface of equal gravitational energy, which on Earth would be basically physically represented by sea level. We look at the equivalent of that on other planets. We can see that most of the other solar system bodies we're looking at here have a single peak, a single mode. So Mercury, Venus, Titan, the Moon, all really have a single peak. The Earth and Mars are slightly different, and they have two peaks. And in Mars, this is thought to be basically just an artifact of a single ancient impact that produces hemispheric dichotomy, where the northern hemisphere is lower elevation than the southern. If Mars had a hydrological cycle, though, this would get erased. There's not really any significant underlying density contrast, or necessarily even that much of a thickness contrast on Mars between the higher elevation region and the lower elevation region. So it's not, the Earth is really unique in having these two different types of crust that have different compositions and different elevations driven by their composition. But, okay, and this is really important if we think about the long-term evolution of the surface Earth system because of the silicate weathering feedback, which I've really oversimplified here in this reaction. CO2 and a silicate equals a carbonate and silica, which is really the major reaction, although usually not with just calcium there. We're talking about lots of other silicates. The reaction that controls CO2 in the atmosphere on long, multi-million year timescales. And how that works, which you folks probably all know, but just for review, silicate weathering, if you have this subaerial crust, which we have on Earth, but which we wouldn't have if we had say a world where the whole Earth was covered in water, we would not have as much efficient silicate weathering, but we do. So when you have this silicate continental crust exposed to the surface, it's vulnerable to degradation, weathering to clays and all by CO2, which provides acidity. The more CO2 you have, the faster that reaction goes, but that consumes CO2. If you're warmer, that reaction again happens faster. And then if you're warmer and you have higher precipitation, that will also increase the weight of silicate weathering. So in all these different ways, increasing CO2, increasing temperature makes silicate weathering go faster, but that consumes CO2. So the whole process is a stabilizing negative feedback. This sort of like the classic Walker 1981 paper. This works in particular on Earth because we have this dichotomy between the oceanic crust, which would be weatherable if you could fit atmospheric CO2 down to the bottom of the ocean. But it's much more efficient when you have a world where you actually do have exposed crust that can be directly weathered by the atmosphere or precipitation from the atmosphere. But this is a bit of a mystery if we consider that in all cases where we have magma going from the mantle to the crust, it's always basalt. It's actually produced in the mantle and going to the crust. We're never producing a granitic magma in the mantle, in the peritic mantle. So why then are we getting this felsic crust in the continents and this mafic crust in the oceans? It's going to have something to do with what's going on in this box, and in particular, it's often proposed to have something to do with the water that we're adding at subduction zones in modern plate tectonics. But there's very little consensus in the literature on when plate tectonics has started. This figure is getting a little bit dated now, 2013, but there's still roughly an equivalent range of proposals out there in the literature today without much more further consensus yet. And sort of directly tied to this, if we're thinking that plate tectonics has something to do with the generation of felsic continental crust, there's also very little consensus on how much felsic continental crust we've had throughout Earth history, and that's also still true today. So some fundamental questions that we can think about in the context of basically large geochemical data sets. How is continental crust produced? How is the composition of preserved continental crust changed over time? And how long has plate tectonics, which probably has some role in this felsic crust generation, how long has this been operating on Earth? So one analogy as to sort of illuminating the usefulness of large data sets here. An analogy that we've been making since I started doing this work in grad school is to the Vostok ice core record here, this famous temperature record derived from basically deuterium isotopes in ice from the South Pole. So you're measuring the composition of ice at only a single place on Earth, but you can get a trend that tells you something about global temperature. If you were to really zoom in on this, just this tiny little window of this data, you might be hard pressed to interpret a trend, a mechanism, a cause for this. But if you have the whole record available to you, you can start to really easily see these overarching trends of glaciation and deglaciation and glaciation and deglaciation. You can infer process from this record. So this is maybe an unfair comparison, but if we go from thinking about the atmosphere sampled in one point to thinking about the crust, the continental crust sampled anywhere we have data, we can look over all of Earth history. This is, in this case, is sodium over time, sodium weight percent. This is sort of, perhaps unsurprisingly, a much messier record. Like, you can't really see any trend here. I can't see any trend here, despite there being a lot of data involved. So do we have any hope of getting meaningful trends from data that's this heterogeneous, where the variation between different places at any one time is much larger than the variation over time? So to try to think about what we can do with this data, there's a few points that really emerged from the work that I've done in this field that I think are transferable to other problems as well, hopefully. One of them is that the choice of independent variable is really critical. So a few slides to show what I mean by this. These are ratios that only an igneous geochemist could love. But lutetium hafnium versus rubidium strontium. And in this first plot, this is binned by this x-axis variable lutetium hafnium. And you can see there's higher rubidium strontium at lower lutetium hafnium. Okay. We could also bin this the other way around, though. We could bin on the y-axis, say that's the independent variable. Well, we get a completely different trend here, actually. So, and both of these are actually really quite hard to interpret, I would say, from a geochemistry standpoint. And the problem is that neither of these are really a good independent variable for this system. So a better one, if we really wanted to understand what's happening with these ratios, would be to look at, say, a cross plot in the same space, but where we're binning by something that's actually an independent variable that has something to do with why some samples are different from others. So in this case, silica. So they're binned by silica here now. The red is volcanic and the blue is plutonic, which you don't really need to pay much attention to. But in both cases, both volcanic and plutonic, you have this initial decrease in lutetium hafnium, which is essentially your lutetium being more compatible than your hafnium in relatively mafic magmas. So you're drawing down that, consuming the lutetium with minerals like, say, garnet, clinopyroxene, orthopyroxene, maybe to some extent. Then as you get more felsic, at some point you're going to saturate zircon, which is going to really consume hafnium very fast. So you're going to turn around, potentially in this lutetium space. You're also, at some point, going to saturate in your evolving magma an alkali feldspar, which is going to have a lot of potentially potassium, rubidium, things like that, or strontium in this case. So you're going to hit this inflection point where you start turning around in lutetium hafnium space. You've got your garnet, you've got maybe some albite, let's say, that contains high strontium, and you're going to go back up in rubidium strontium. So you could come up with different scenarios depending on which minerals are in a given system, but at least you have a chance in this case, and it's because we're actually looking at something that is an independent variable for this system, or is closer to the true independent variable, which would be degree of differentiation. Okay, that's maybe a long example, but one tangent from this is that time is always a valid independent variable, because nothing else is going to be changing the time at which things happen. Time is flowing off its own accord, and the geochemistry can change over time, but if you bin by time, that's always a fair thing to do. Whereas binning by some other geochemical variables may not actually be telling you anything about your system. Okay, another point that I think is really important, or another, using points twice here, but another concept that's really important is that geochemical distributions are really, or geochemical data are really distributions, not points. So if you get a single number reported in the spreadsheet for, say, lanthanum in this rock at a given time, that's not just a number, it's a distribution. It's a distribution in at least 2 dimensions. So one would be the lanthanum content is itself uncertain. Really, you've tried to estimate lanthanum of your rock, say by mass spectrometry, ICP-MS, INAA, some whole rock analysis technique, but that's got uncertainty on it as well as a number. And the age of the rock also has an uncertainty on it as well as a nominal value. And if you only look at the number, which was surprisingly common in geochemistry in the past, you end up missing a lot of the picture if you ignore the uncertainty, if you ignore that these are distributions. So just a somewhat oversimplified example here. Say we've got this data, it's measured in rocks of various ages. Some are from all the same formations, so they're all lined up in the same place, and then values over time. If we were to just bin these as such, we could argue that it increases from 22 or 2025 to the next time bin, and then decreases. But what if the time uncertainty on these points is huge? The time uncertainty on these points is larger than the bin, which is actually not uncommon because it's really hard to measure time, depending on what sort of temporal scale you're going to want to bin your data by. Really, you should think about representing that uncertainty, and you can do this lots of ways. You could do that by actually calculating out the Gaussians by hand, or maybe a little easier, you can do it by just sampling from that data set, drawing random points from the distribution. In this case, both of the 2 dimensions we're looking at. And now if you were to bin it, you'd get a rather different trend over time. In fact, in this case, much less of any trend over time. But that's helping smooth out noise that is not actually telling you about the system if your X uncertainties are actually that large. One more point that I think was sort of a common mistake in geochemistry in the past, maybe will be less of one going forward, but it's basically that the natural statistic for your distribution may not be the natural statistic for your physical system. So what I mean by that is many geochemical data follow, say, a log normal distribution. So in this case, some hypothetical trace element value could be in, let's say, parts per million. You have many data on the lower side, fewer on the higher side. And if you were to zoom in on this, people will often, given that we know that the natural statistic of a log normal distribution is the log mean, we try to look at the log mean, the geometric mean of that data set. That'll give us this value about 1 in this case. We could also look at the median, which is sometimes preferred to the mean with the idea that it's less sensitive to outliers, sort of much like the geometric mean. Okay, these are both giving us values around 1. But what would we get if we were to take all of the rocks represented by this distribution and physically mix them together? Take all of the crust this represents and put it in a giant continent-sized blender. We would not get either of these values. What we would actually get would be the mean, which is way up here, near 7. So even though the geometric mean is the natural statistic for this distribution, which is log normal, it's not the natural statistic for your system if your system is continental crust that is actually getting mixed with other crusts, say. Magmas. It actually is quite general, but it's a common problem. Okay, so coming back to our geochemical data set here, and this here, sodium over time, not seeing much trend. What can we do about that? So a few take-home points here at this stage. One is that time is a useful independent variable. We know it's going to be independent, but you need a long record. As we just saw, though, we can have a long record. We can have 4GA and still not really get a usable answer from that, just plotting it. Another point, sort of a really oversimplified one, is the atmosphere is much more well mixed than the lithosphere. You can measure the atmosphere at one place and have it tell you about the whole globe. You very much can't do that with the lithosphere. And this averaging is actually useful if you want to look at global trends over time. So if we want to make an equivalent record for the lithosphere to tell us, say, about the temperature of the mantle over time, the secular cooling of the mantle, we're going to essentially have to do that mixing ourselves. We're going to have to do it manually. So we proposed back when we started this project that by gathering as much unbiased data as possible and building a time series throughout Earth history, we could try to see through some of this vertical scatter, this heterogeneity of the rock record, identify long-term trends that might tell us something about how the continental crust is produced, how it evolves over time, and all that. So we need igneous data. We need to know where it is. We want age constraints. We got it from many sources. largely EarthChem, which is a free public data set still up there, which in turn gathers from NavDat, PETDD, GeoRock, the geological surveys, all that. There's a lot of data that's not in here, but there's on the order now of perhaps 1 million total whole rock geochemical samples in there of different various rocks from around the Earth. So these are the 66,000 or so that we're 67,000 or so that we're using in this first example here. You can see it's definitely not even over the globe, but we at least have every continent represented in some form or other, and every tectonic environment represented in some form or other. So the first technique that I started doing to represent any of the uncertainty in this data and represent some of the try to fix some of the spatial bias in this data was what we called weighted bootstrap resampling. Mathematically, it's really pretty crude. You could probably do more sophisticated things these days. But the weighted part of this is that, say you have a cluster of samples, all sampled from the same region where, say, the rocks are really interesting for geologists, there's mining there, there's some reason to study this area, and we have really high sample density. Adding a single new sample from that region tells you less than adding a single new sample from somewhere on your continent that is completely undersampled or completely unrepresented, if what we want to know is the average of the whole crust or the whole continent. So what we can do is essentially give higher weight to the samples that are less well represented in the data set and lower weight to the samples that are really densely represented in the data set to try to even some of this out. This whole process involves, you calculate your weights, you resample in proportion to the weight or the inverse of the density, basically. And when you resample, if you just add Gaussian noise, that's a really simple way of propagating the uncertainties that we know each datum has. So you can then bin this by your independent variable to basically reduce the noise, try to increase our signal to noise ratio, and try to get some average, which might change over the independent variable, in this case, time. And if you basically want to repeat this many times, if you're using this to propagate uncertainty, which we are here. So here's an example of what this looks like. Raw data on the left, resampled. Essentially, many of these vertical bands here that have very, very high age uncertainty get smeared out, which is effectively representing the fact that we're less certain about when in time those rocks are actually from. And then if you take the binned means of this, you can now finally start to see a trend over time in this geochemical variable. So we've had to do the averaging ourselves, but we get a signal. Okay, so coming back to our problem of the two types of crust, where it's coming from, as a reminder, our problem is that this primary flux is basalt in both cases. So let's start by looking at the basalts over time and to see if that tells us anything about how tectonics has changed over time, say. So if we look at the basalts, at the major and trace element concentrations, one of the most obvious first results we saw was that basically compatible elements, those that would rather stay in the mantle when you melt the mantle, those were more abundant in Archean basalts and less abundant in modern basalts. And incompatible elements, which would like to go partition into the melt, are more abundant in modern basalts than Archean. So this is all 43 to 51% weight silica rocks from this data set going through all the resampling. I think you folks all know this because this is a geology university, but geology department. Compatible elements are those that would rather be in the mantle, and compatible would be in the melt. If you increase more, you're basically diluting your compatible elements and diluting your incompatible elements as you melt more of your mantle into this magma. And for a compatible element, you have to melt to force that compatible element that would rather stay in your prototype into your mantle. Okay, so this is sort of expected. We can try to calculate an actual temperature from this using something like melts. So the approach I took back in grad school was to take a mantle prototype composition, melt this 1, 2, 3, 4, all the way up to 100% synthetically, in this case with P-melts, compare the simulation result to all the observed composition for all the observed basalts, see which melt extent fits best for each composition, and then put that up through all the resampling and get a mantle melting extent trend over time. And basically this agreed with what we expect from the Earth being hotter in the past, because we know the Earth accreted hot and a higher radiogenic heat production in the past. So the direction is expected. There are a few features which are more surprising, like this jump right at about 2.5. That's sort of strange. The mantle is huge. It can't just cool off suddenly. So we were wondering what might be going on there. At the same time, we also noticed that a lot of trace elements in the basalts changed rapidly around 2.5 billion years ago. And that, there's a whole range here, mostly rare earth elements, but you can see it also in things like zirconium, which is an incompatible element. There's this rapid change around the end of the Archean. So just in case there are people here who are not geochemists, from the data science side, lanthanum and ytterbium are two of the rare earth elements that the igneous geochemists really use often to tell them about what minerals might be being removed from the melt. So ytterbium is very compatible in minerals like garnet, lanthanum less so, and other than their size, which is the ytterbium is smaller than the lanthanum because of the lanthanide contraction, other than their size difference, they're very similar. So geochemically, there's not a whole lot that's fractionating them, these rare earth elements, except from each other, except the size and the few that have different charges. So lanthanum ytterbium ratio, usually a higher one might suggest more garnet is being removed, or a lower one might suggest more garnet is being added to your melt, something like that. There's this rapid change here at the end of the Archean. We can try to model this with, if we pick any partition coefficients we like, let's try to make the Archean fit well, and then apply the melting extent we saw before. We can see that we have a mismatch in the modern. If we try to make it fit in the modern with any single pair of constant partition coefficients, then we get this mismatch in the Archean. So something is significantly different here. One of the first things we thought might be going on is that this could be, say, an onset of plate tectonics. Let's see, how's our time? Getting there. So that was a first possibility, but as we looked into this more, we thought if that were happening, if this were an onset of plate tectonics, we should also see a big change in slab fluid mobile element abundance from slab melting. So if we go back to our periodic table here, there's a sort of really first order simple trend in the fluid solubility of elements as a function of their size to charge ratio. So things on the far left with a very low charge and a large ionic radius are very soluble in aqueous fluids. Things with a high charge and a low size are much less soluble in aqueous fluids. That's true at the surface, but it's also true at elevated pressure and temperature in the conditions where you might be removing fluid from subducted oceanic crust. Here's a Tatsumi 1986 paper which shows this experimentally. So your cesium and rubidium are very fluid mobile, very fluid soluble. Your niobium, ytterbium, things like that, much less fluid mobile. So we should expect to see, and say something like your rubidium niobium ratio, you should expect to see this big increase at the end of the Archean if this jump in these other trace elements was from the start of plate tectonics. So here's niobium thorium, just to start. This is a really classic one in the igneous geochemistry literature because niobium and thorium are both have relatively similar partition coefficients between mantle and basalt. In the minerals that are common in both mantles. So they shouldn't be fractionated from each other by igneous processes very much, but they are different in fluid solubility. So here's our end members. If we plot our averaged, weighted Bootstrap resampled data over time, we see we're consistently more on the arc side here than the rift side, and the non-arc side. Okay, so that's not looking likely for our subduction initiation. What if we try a more dramatic contrast, rubidium, highly mobile versus niobium, highly non-mobile? Again, through time, we're consistently more towards the arc end member. And one more proxy we can use, jumping from trace elements to major elements, this tholeiitic index, which is essentially the concentration of iron in samples with 4 weight % magnesium divided by those related samples with 8 weight % magnesium. Essentially, the wetter you are, if you're in an arc sample, that tends to cause calc-alkaline differentiation in which you saturate magnetite and ilmenite early because of your or early relative to your other silicates, your high water content and high oxygen fugacity, and your iron goes down during differentiation. So you get a fulletic index less than 1. In dry magmas, you don't saturate your magnetite and your oxides early, so you actually increase iron with early differentiation. So you're above 1 here, this ratio. This is going to be very hard to alter subsequent to the production of these rocks, because these are major elements that are, you just math balance wise, it'd be hard to alter this in older rocks compared to a trace element. But again, we're consistently on the arc side throughout essentially the entirety of the preserved rock record here, back to roughly 3.8, 3.85 GA being the oldest samples that are really abundant in this data set, coming in this case from Ishua. So I think this is not very consistent with these first 2 options for what could be going on with these other trace elements. And instead, we need to look for something a little more complicated in terms of mantle melting systematics. So as you melt basalt, as you melt peridotite, start at some solidus, increase temperature, your melt fraction increases, but doesn't increase linearly. And there are things like, say, inflections here when you run out of clinopyroxene or garnet, phases like that. So this nonlinearity actually helps fix this sort of jump we saw at about 2.5 GA in the melt percent. There's actually no jump in the inferred temperature from the same model. That's good. We don't have to suddenly cool the mantle or anything like that. And we don't have to suddenly change the composition of the mantle either. We don't have to suddenly, say, change from a dry non-arc melting to a arc flux melting, which would potentially change the composition of the mantle, the produced basalts. Okay, so we don't have to change the temperature or anything weird like that. What we do end up changing is the partition coefficients of all of the trace elements we might care about from the mantle to the magma, to the basaltic magma, because at higher degree melting, we eventually run out of some phases. So say this clinopyroxene and garnet here at about 2.7 gigapascals are both depleted in an average parcel of primitive mantle once you've extracted 27-30% melt from it. And that's going to change the partition coefficients. And that's then interesting. If we look back here, where is our 27-30% melt? We're actually close to this Archean Proterozoic boundary here, interestingly enough. So we can just go ahead and model this. We can look at the mineral melt partition coefficient for all of these minerals, for any elements we might be interested in. Here's lanthanum and ytterbium, for example. And you can see this big kink in the curve when we run out of garnet and clinopyroxene. If we then combine these with our mantle melting extent, we can start to get a curve that actually fits quite well. So we can explain these abrupt trace element signatures at the end of the Archean without needing to do anything really dramatic to the way magmas are produced, without needing to, say, initiate tectonics at this time. This works for a lot of other elements as well. Okay, so coming back to our questions here. From this big data approach, I would argue that we clearly see that there was evidence of higher degree melting of the mantle in the past, but it's not necessarily being melted on average by different processes. We still have some flux melting in subduction zones and some dry melting in rifts and plumes, perhaps, in roughly equal proportions, all the way from today back to 3.8, 3.85 GA, possibly even before. We just don't have rocks in much abundance from before. Okay, so this is work that's been out for quite a while on my side. So one sort of new tangent from this is, well, if plate tectonics has been operating the whole time, shouldn't we have had essentially felsic modern like crust, continental crust the whole time? I think yes, we should, but there's been quite a lot of literature arguing that early Archean continental crust was much more mafic than modern continental crust. So Dweem et al., Tang et al., there's dozens of these almost that have argued traditionally that Archean crust was in bulk more mafic than modern crust, and that it potentially too mafic to have been produced by modern style plate tectonics, thus arguing that there was no subduction in the Archean. I think I'm not going to have it to go through all of these, but just to pick one example of how some of these traditional studies have been wrong, in my opinion. So this is from Dweem et al. Rubidium strontium. So there's many papers that use proxies for silica composition of the continental crust, rather than measuring it directly. If you do just look directly at all the preserved Archean crustal rocks versus modern crustal rocks, you get actually pretty similar silica. But there's reasons why that could be wrong from preservation bias, say. So people have used a lot more indirect records. In this case, Bimodal used strontium isotopes and rubidium-strontium ratios in whole rocks to try to estimate essentially the rubidium-strontium ratio of the protolith from which they believe that rock was formed. That you say a more mafic protolith that was remelted to produce a granite, something like that. And they can estimate this protolith rubidium-strontium ratio. There's some uncertainty in terms of, because there's model ages involved, hafnium model ages and rubidium-strontium model ages actually in this case. But they get a trend that's statistically robust, actually, this stage 1 rubidium-strontium over time. And then they go ahead and extrapolate that to have a direct mapping, basically, to silica based on this curve on the right here, which is based on modern rocks. So more felsic rocks have higher rubidium-strontium, so they can use that to infer that modern crust is more felsic than Archean crust. Okay, well, but we have a lot of data here. So what if we just look at the ratio between rubidium-strontium and silica in modern rocks versus Archean rocks? So this is again using the weighted Bootstrap resampling and all that. What we can see is this trend is very much not the same through time. So Archean rocks had much less rubidium in them and a lower rubidium-strontium ratio than modern granites, say, at a given silica. So at 70% silica, we had maybe a third as high of a rubidium-strontium ratio in Archean granitoids than modern granitoids. So that's really changing our mapping between, if we're trying to then go backwards from rubidium-strontium to silica, we can see we have low rubidium-strontium in the Archean, but that doesn't necessarily mean we had to have had lower silica in the Archean. So one way to sort of test this in a more forward way is to say, what if we just took a similar mixing of basalts, andesites, dacitites, rhyolites, basically mafic to felsic, all the rock types we have, sample them in the sort of modern bimodal proportions that we see in modern continental crust, and say, well, if the Archean continental crust had the exact same silica distribution, what would the rubidium-strontium ratio of that average crust look like? And that's a pretty simple calculation, actually. And one little feature I want to highlight here is that this 1 to 2 GA curve actually has anomalously high rubidium-strontium, sort of around 65% silica in your maybe granodiorites. I think this is actually potentially biased, actually, in relation to this famous A-type granitoid track that goes across North America. There's a 1960s or 70s paper about these essentially A-type-esque granitoids that form a linear feature going across the US. And since the US is kind of overrepresented in our data set, this feature, I think, shows up here basically in this 1 to 2 GA time bin, that we have anomalously high rubidium, anomalously high rubidium-strontium ratio in this sort of 1 to 2 GA bin. So if we then go to rubidium-strontium again, we've got on the left here this juvenile rubidium-strontium. On the right, this constant silica rubidium-strontium model, null hypothesis, we could call it, if the continental crust had constant silica this whole time. And what we see, actually, is that these two match very closely in terms of pattern. I should note that the absolute scales are different here. They both are 0 at 0. Our observed constant silica rubidium-strontium is much higher than the quote-unquote juvenile rubidium-strontium, but that's essentially because we're comparing the final rock to the protolith in this case. And there's various other issues with the model age approach that introduce some, I think, absolute uncertainty. But in terms of the pattern, we get very much the same here, which I think is essentially telling us that we don't need to change silica at all to produce a rubidium-strontium trend that looks like this over time. And in particular, this high peak at this sort of 1.4 GA is, I think, potentially attributable to the A-type anorganic granite track, which, I mean, it is actually quite large. So I don't know how much of that is bias and how much of that is the real composition. The real global average actually was higher at this time period. We try to correct for the bias, of course, but we can never be sure. But in either case, if it's whether it's bias or real, we get the same result as Dweem et al., but without requiring any change in average silica content of continental crust between now and the Archean. There are similar arguments you can make for many of the other trace element ratios that have been used to estimate Archean continental crust composition, and then there's a whole second set of arguments that come in for redox sensitive elements, which have been used in shales and many studies that have argued for a more mafic Archean crust. So there was a preprint that was sent out to you folks that you can look at if you want to see more of the details of how this might apply to other estimates that have resulted in a mafic Archean crust and why they might be inaccurate as well. But just to cut to the conclusion, I think what we see from the EarthChem data set, when we fully take account of not only the variation in element concentration over time, but the variation in the relationship between elements over time, your rubidium strontium at a given silica. I think that's much more consistent with these newer estimates by, say, Graeber or Ptacek, who I think you have also had speak recently in this series. I think these estimates are likely much more accurate, which would suggest that actually we had similar to modern crust for much of the Archean. And one quick point I'll add for this Graeber paper, this is titanium isotopes. There's a potential issue with that in terms of calc-alkaline versus thallitic differentiation, which could cause inaccuracy in that. But if, as we looked at a few slides ago in this, say, thallitic index, the proportion of that has actually been quite constant over time. So I think this Graeber estimate may actually still be valid if we are correct that the proportion of flux and decompression melting, the proportion of arc and non-arc melting, has been roughly constant throughout this whole time period. So I think I've been talking for a while. I should probably leave it here. I'll leave you with a few other take-home points on geochemical data science in general, and I guess pass it back if there are questions.
Okay, thank you very much, Brenhin. It's great, and since we record your talk and also we record the Ptacek's talk, I think the link is also in the sheet that I shared. So it's pretty interesting, and then unfortunately he's not here in the audience because he would be very happy to hear that you all. Because we used to, because before we have, it is great that we have a very diverse different ideas of people in the group. Okay, now it's time for questions in the audience, please. Please please open your mic and ask questions.
Hi, I'm Qinben from Zhejiang University, and I'm a first-year PhD student. I got a question about the before you talk about the global map. There's a slide is the global, and you add weight at different part on the continents, right? Yeah.
Yeah, I went over this a little too fast, probably. Way back here. So this is all the way back from 2012. So I didn't go into it very well, but so the idea is that a place that is less well sampled will be telling you more about the average than one more point from a place where we already have many points.
Maybe I was thinking maybe the low weight, the sample, maybe some few million years ago, it's not there. Maybe he's in the continent. I don't know how to understand that.
So what was the part you said about a few million years ago?
I mean the sample point. I mean the rock you mark low weight. It is here now. Oh. Maybe long time ago.
Right. Okay.
It's not there.
Gotcha. Yeah. So right. So the picture only really shows you the spatial part of the weighting, but there is also a temporal side, which is if all of say all these low weight samples were actually of wildly different ages. You know, they were, some were 4GA, some were now, whereas these two samples over there in the middle of nowhere were all the exact same age. That would actually change the weight calculation because we also want an even distribution in time. There's another problem, though, that I think you're bringing up, which is one we can't solve at all with weighting. We really have to live with, which is that there's preservation bias, too. So we can try to undo sampling bias to some degree, or at least reduce the effect of sampling bias by not having our result be totally dominated by the few places where people have decided to take many samples. But there's nothing we can do about the case where there was a rock that existed 2 billion, 3 billion years ago that is just not there today. We can try to reduce the bias towards, say, modern samples. You know, say we're looking at a low weight sample and, you know, many of them were all produced in, say, the last 10 MA because we've really sampled modern volcanoes well. We don't want those to dominate the estimate either, so those get downweighted as well. But binning by age, that's less of an issue. Preservation bias is kind of the one that we really, there's nothing we can do to bring back a rock that used to exist that is now gone. The one other technique people have used is looking at sediment as a record of what has been eroded in the past and hope that records rocks that may have been lost from the crust, though only those lost erosionally, not things that have been delaminated. Those we have almost no idea what we could have had from that. So because it's such a hard problem, I don't know if we can really even estimate the uncertainty. So, you know, the 2 sigma standard error of the means in all these plots aren't representing the sort of more philosophical uncertainty of what rocks might have existed in the past that are just now missing because they've been destroyed. So that uncertainty is on top of any of the uncertainty shown in the plots here. But we can basically just try to do the best we can with the data we have.
Okay. Yeah.
And sampling more samples is always better. So yeah, there could be a very important composition that it does exist, is preserved, but hasn't been sampled yet. So more data is better if we know the uncertainties on it.
Yeah, okay, got it. Thank you.
Thank you.
Okay, more questions? Yeah, I think for sample preservation problem is a question we ask for any geology talk or archaeology talk about how well that is represented in what you want to say or want to present the question. Yeah, more questions.
Yeah. I can put in a quick advertisement for 2 other, you know, much more technical CS points that I think are going to be important in geochemical data analysis, but really in all data science going forward. One of these is automatic differentiation, sometimes also called more broadly differentiable programming, which is when your entire program, including, say, control flow, can be differentiated. You can calculate a derivative on it. There's a lot of languages where this is possible. So the JAX subset of Python allows this. Swift for TensorFlow, which is one of Google's big efforts these days, allows this. But the language I mostly use this in is Julia, which is basically a just-in-time compiled language that's designed for numerical scientific computing. The second point is really much more specific to Julia. There are a few other languages that have this, a few Lisp dialects that have multiple dispatch, but it almost always comes with performance overhead. Multiple dispatch it's a pretty simple concept. It's when different data types can be valued by different functions based on the type of data, and it can occur for any data type. I don't have a demo prepared for this. There's a great YouTube talk by Stefan Karpinski called the Unreasonable Effectiveness of Multiple Dispatch, which explains this really well. Basically, it allows it. You wouldn't necessarily expect it, especially not if for someone like me who didn't come from a computer science background originally. But this really allows for amazing composability between different scientific packages. So if you write a package to do one thing, and someone else in a different university writes a package that could say use your data type to do some calculation, if you work with multiple dispatchers, a very high chance that those two will basically just be able to work together without really much explicit intervention. So that these are basically the reasons that I've been switching most of my scientific codes over from a mix of MATLAB and C over to Julia. But I think regardless of language, these are going to be important trends in data science in the near future.
Okay, I have a question. Actually, this question was almost the same question I asked last week for last week's speaker. So when you choose a compatible element and an incompatible element, well, you could choose lithium, etc. So my question is that, like I say, there are so many compatible elements that you can actually evaluate it from. So the answer that from Patrick last week was that, yes, he considered a whole bunch of combinations. For example, he chose 16 of them and two combination pairs. And of course, he said that, of course, we should consider all the combinations other than two combination out of the 16 should be P15, 16. And all the possibilities, and other than don't have to limit to 16 elements, it should expand much broader spectrum as he listed there, but there is just not enough computational time in doing that, or his own time doing that. In fact, he said it's worth trying. So I'd like to see what's your perspective that when you choose the hafnium, when you make the choice, that I don't know that how did you make the choice to pick up the elements to make those plots and then derive your conclusion?
Yeah, so a lot of the when I was showing single elements, a lot of that was based on sort of a traditional igneous petrology approach, where there are some elements where you understand their behavior better than others because with certain elements or ratios, sometimes you're able to avoid other complicating factors that are, say alteration or other fractionation that's not what you're looking at. But ultimately, I think there's a lot of appeal to an approach where you look at everything. So especially for compatible, incompatible element, say abundances. If you're trying to do something like this, where you're trying to estimate silica from trace elements, doing it with just one element, this rubidium strontium, that's really risky. That's really dangerous. I think that's kind of the underlying flaw in a lot of these older papers that proposed a mafic continental crust, is they picked one ratio or two ratios or three that they could use to try to extrapolate from trace element composition, say, of sediments to bulk igneous crust. And many of those are susceptible to bias. Some of them, it might be like what I was showing for rubidium strontium. For others, it's more to do with fluid solubility in the surface environment if you're looking at a sedimentary rock, and how that changes as a function of redox, because the GOE, the great oxidation event, is right around the same time that people are often interested in plate tectonics potentially changing style or starting or whatnot. So you're more robust to those types of errors the more elements you use. And I think to some degree that's why studies like this one by Felsic, or there's another, I think, Graeber one that was also on trigonous sediments using multiple ratios, why those got closer to what I think is the right answer. I think that's because the more elements you have that are behaving differently, that have different sets of biases in them, the more likely you can cancel out those biases by averaging and increase your signal to noise ratio by averaging. So I think that there are still cases where you need to be careful about which elements you use in terms of element pairs or element ratio pairs where you can sort of a priori exclude certain biases. But in many other cases where there's going to be random noise in each ratio, the more you can use that are telling you something about what you want to know, the more ratios you can use, the more elements you can use, the more accurate your results should be. I'm sure we'll be seeing more of these sort of multi-element approaches as geochemistry becomes more computational and people are less limited in terms of technique and computational power.
Yeah, this is just my comment that that's so a trend of the geochemists too, that but when I look at how people get those ratios or ideas, normally those or get from, let's say, certain set of field work samples, or they are from experimental petrology work, for example. And with that characteristic is that if you happen to be very lucky in a one field site, then you happen to see 2 or 3 elements or 2 or 3 ratios that works out pretty well. And in experiments, that's my PhD work, experimental physiology, that we love to only change one parameter to see the effect of X on the effect of Y, because that's something easy for you to control. But however, in the real world, that is a multi-high dimension system. Then the problem is that a lot of this simple system, simple mechanism, won't solve everything. That's why that when we plot the entire data set, in almost all the major geology questions, we will see like a mess. And if we do it in 2D or 2 ratio plot, it always looks like a mess. However, for multiple mechanisms that work together, actually in the high dimension space, it doesn't have to look like a mess. Like the recent work that we have almost accomplished, that we find that for hydrogen diffusion or hydrogen site that are staying in the different defects in the crystals, they have many different possibilities, possibility A, possibility B, possibility C. So it used to be that if one researcher is happen to collect 20 samples in one field site, and then all of them happen to correspond to defects A, then he claim, okay, A mechanism works, then B says, no, this B works because he happened to take samples for that. Then for somebody come in to take a group of sample that happen to have exactly the one sample have the FTIR measurement, this combination of A, B, and 3, then it's very easy to get confused. So which one is the dominant, like how that works. But when we plot it together, all the data in the 11-dimension matrix, actually when you use SVM, it's surprisingly good that they are really separated into 2 classes. And it's quite surprising to us that the result is much better than what we originally thought. And then when we compare it with the previous people's work, like diffusion compositional profiles, and to see some grains, some points are diffuse, some points are not. Actually, it agrees very well with our, let's say, the high dimension SVM results. Actually, it has a very wide implication for the ones people already identified, or for the ones that people just don't know because it's just a mess in terms of the 2-dimension plot data. So as from my own perspective, that with time going on, more and more high dimension possibilities we are going to be discovered. And then later on, people were coming back to look at, okay, what's the real cause and consequence behind it? And to me, like Luthien and Hafnian, I don't know that the whole first person ever on this planet ever plotted, but I don't think that is the one who does the theoretical chemical computation person who knows everything about the atom as well electron and structure to do that. But the problem is that there are some geochemists that they happen to get something plotted that looks like, okay, this too looks like a correlation. Then they read a paper. Then more people find that, okay, it also showed in my samples. Then let's read this paper too. Of course, compatible, incompatible. This idea is not too hard to, let's say, to do that. So I think even by that, the ratios we have geochemists plot so far are very empirical at the very beginning. So actually, we are doing almost similar approach by doing high dimensional thing, find some empirical evidence, and then we come, let's say, it's actually, to me, it's a very similar approach as what we did before. But just to first explore more. Sorry, I went a little bit too long. So okay, do we have more questions? Actually, we ran out of time. It's already 10. We could take one quick question, if possible. Tao, do you have any questions?
Hello, Professor Keller. In 2018, I have sent an email to you and asked questions about the Bootstrap resampling method because at that time I've started my new master project, and you generally give some useful suggestions for my for the Bootstrap resampling method, and it's great to listen to this talk. And for me, I think for the arc and non-arc sites in the history of the Earth, recently I used the dataset from the georock and scan. I found that usually we think we will get some the ratios like the lower, the lower nabinium and the I think the ratio is the symbol of the I don't know what's the English because the English name of the elements is the N B.
Niobium. Niobium. Yeah.
Only niobium is really lower compared to the neighborhood elements like the lanthanum. Yes, the niobium ratio is really low in the oxide, and the non-oxide like the intraplate intraplate volcanics. These rocks, the basalt usually possess high ratios, niobium to lanthanum ratio. I used the dataset to calculate this ratio, and I found that in the Archean time, the ratio is relatively low.
Interesting.
Yeah, I don't know how to interpret it because in Archean we usually think that the plate tectonics may not be initiated, but the ratio is relatively low, and I don't know how to interpret it, and or the plate tectonics is already initiated at that time, or other explanations could be addressed.
Interesting. Yeah. So there's always it's always interesting variations here. So the one thing I can add that might be helpful, just if in terms of reproducibility of
the proportion
what I have here. Let me see if I can just get this up here. Let's see. So on let's see, I can share this here on my GitHub here. Share the desktop. Hopefully that works. If we go to this this repository here, hopefully this works. So there's some demos here, which should at least let you try this. Say if you want to try this approach, but on your own data set and see, does Bootstrap resampling like this matter, or are we implementing Bootstrap resampling in the same ways? Any of those questions. If you open this this binder notebook, this should actually run in browser without you having to install anything, and you can scroll through there, and you can actually paste in a separate data set if you want, or this one will download. This will download the data set I've been using in here, and then run on that data set. So yeah, if we're seeing different things, I'm always interested to talk about it. But this could be a useful resource in terms of if anyone's curious to reproduce any of the trends that I showed today. You should be able to reproduce all of them either in this notebook or for the constant silica in this notebook. I don't know if not every figure will come up automatically, but all the tools are there such that you can run these in the browser. But always happy to talk more over email. This is the data set that I have is certainly not the be all end all of data sets, but we'll see as more data do become available, and as we continue to sample the Earth better.
Yes, I just use the MATLAB to write the codes, and also the Julia is better, I think.
It has some interesting features. There's a learning curve, and there is a lot of this like compilation latency when you get started, which isn't in MATLAB or Python, and that can be something to get over. But once you get used to it, I think, and there's a package revise.jl that reduces the need to reload and re-experience that compilation latency every time. That makes revising your code faster. I think it's a good way to go. I mean, MATLab's not going anywhere. Python's not going anywhere. These are all good languages, but I've really been enjoying doing it in Julia, that's what these notebooks are.
Yeah. Those coding software such as the tools, which actually in our program we have many experts, that students that really get used to feel comfortable with almost any language.
Yeah.
A coding language that's available in the market as long as there are. So this is not a big problem, especially many students have extremely strong coding background due to their own major or work. Yeah. Okay, nice. Great. Thank you very much, Brenhin, and thank you for your talk. And I hope that after epidemic, you could find some time to visit us on site and give another talk, seeing some real person rather than the visual ones that you don't know whether the artificial intelligence is talking with you or not. So yeah, thank you very much. We have recorded your talk and we're going to send you the video link after. Great. Thanks for having me. Thanks everybody for joining.